Okay. We're going to skip one more section of Chapter 8. Very, very small section, but it's enough that I don't want you guys worrying about it. 8.3F, Section F, it's looking at oxidation and reduction reactions. You don't need to worry about that section, just so you're aware. So if you see homework problems based on that, they probably do show up. Just don't worry about those oxidation reduction reactions. Okay? We'll talk about that after the exam. We looked at nomenclature. Whoops, that's resonance and mechanisms. So you will see mechanism questions. You will see resonance questions. Absolutely. Okay? So you must be able to show how to move electrons appropriately. Always start your arrow at a source of electrons. Okay? What's a good source of electrons? Okay? A bond. I can kind of accept that one for a mechanism, not for resonance. We look at resonance, source of electrons. Okay, we're looking for lone pairs. That was not what I wanted to do. So we could look for a series of lone pairs. What else? Or we could look for a pi bond. Okay, those are your two sources for electrons. Something that might stand out even more. This can be kind of funny, just because I saw I can do this. Negative charge, right? Those are going to be good sources of electrons. Doesn't that look kind of funny? It's like a little face. Yeah. Sorry. Yep. So, negative charge, lone pairs, pi bonds, all of those are really, really good sources of electrons just in general. Okay? So even when dealing with a mechanism, those are a good place to first go to find electrons. Okay? When you're dealing with with mechanisms, you might end up shifting into the sigma bonds, okay? But that should be a secondary consideration. If you have to break a sigma bond, that's when it's okay to break it. Otherwise, you'll be focusing in on your pi bonds when you're breaking bonds within mechanisms. Okay? So if we had a general example here, I'm going to pick a negative charge and a positive charge. And if I want to connect those with a mechanistic arrow, what would that arrow look like? From the negative to the positive, where's the arrowhead? At the positive end. Okay? I want to make sure we're absolutely clear on that. Absolutely, we'll see questions on that. Okay? It would be intended to be an easy answer kind of question. Okay? So please don't mess that up. That allows you to figure out your reactions. So if you can follow negative to positive, you don't have to memorize things because you can use that information to predict or derive your answers. Okay? So please, please, please draw those appropriately. We talked about nomenclature. Did you guys attempt nomenclature for alcohols and amines? Any questions about that? Were you guys all okay with doing the nomenclature system? At least close enough. Okay, we'll go ahead and move on. We looked at bonds and forces. Again, I wanted to put it up there because I think it's important. Okay? If you find a particular type of bond, that's going to tell you some information about the intermolecular forces, which will also allow you to predict something about its reactivity. If we have something that's extremely polar, say looking at ionic situations, okay, we're now going to predict some strong interactions because we want to neutralize those charges. Everything's trying to neutralize the charge as best as possible. Okay? So if we've got ionic charges or if we've got charges in general, that's an inherently bad thing. What we're going to try and do is stabilize them in some fashion. Okay? So where we ended on Tuesday was with this slide, right? Okay. So what we ended up doing was evaluating each of the different types of functional groups we've seen so far. Your alkanes, your alkyl halides, and then we introduced two new concepts, your alcohols, which was Chapter 8, and then your amines, which is Chapter 9. Okay? Whoops, that's 10. Okay, your amines are chapter 10. As far as the information that I want you to get out of the amines, it's pretty much going to come down to one section, and that being that your amines are basic. Okay? That chapter goes through a whole bunch of nomenclature, and it gets irritating with the nomenclature with the amines, but it's just nomenclature. As far as the chemistry goes, it pretty much only addresses that nitrogens are basic, and that's about it as far as the chemistry goes in that chapter. Okay? It does go through some other things that we'll address later when we talked about other material. Okay? Questions on this slide in general? You guys can all do the interpretations that we talked about. So we're going through, we find differences in electronegativities. We evaluate that bond, evaluate each atom on it. So if we looked at, say, the oxygen, okay, we know oxygen is more electronegative than carbon. So oxygen builds what kind of a charge? A partial negative. What happens to the carbon? Builds a partial positive. What happens to the hydrogen on the oxygen? Also a partial positive. Each of those partial charges is what generates the reactivity that we refer to down at the bottom. Okay? So our hydrogen being partially positive correlates to which reaction? That hydrogen being partially positive correlates to an alcohol acting as a Bronsted-Lowry acid. Okay? If we take a look at the, might as well use colors because I got them, the partially positive carbon, what does that correlate to? It correlates to our electrophilic carbon. Okay? The partially negative oxygen, what does that correlate to? We have a nucleophilic oxygen. How would we know it's nucleophilic? When it reacts with something other than... So what would the atom be other than? Other than hydrogen, it would be a nucleophile. If it instead acts with hydrogen, we've got our Bronsted-Lowry basic oxygen. Okay? So the idea is to look at those charges that build up, where they're coming from, what we can do with them in each individual circumstance. Okay? This is ultimately what when we went through functional groups way back what I was trying to get you to do when I said point out the reactivity. It's evaluate each of those charges and see what it can do. What are the definitions of each of those? Okay? So, the next big fun thing that's really going to come in with this exam is looking at an individual reaction. Okay? So, given a reaction, you should be able to classify it based on groups. And since I can walk, I'm going to walk more. Okay? So we should be able to go through and decide what's happening in each of these individual steps. Okay? So let's pick that first reaction up at the top. Ooh, zoomed in too much. What we'll do is go through and find the bonds broken and the bonds formed and try and come up with something that best describes that interaction. Okay? So what bonds were broken? Okay? We lost the carbon-iodine bond. Okay, did we break any other bonds? No? So what other bond or what bonds were formed? We've got the carbon-chlorine bond. Okay, so that's everything that's happened. All we're doing is comparing across these reactions. Now we try and come up with a term that best describes that. Okay, what's the best way to describe what occurred there? Substitution. Okay, we swapped one piece for another. Okay, what happens in that second reaction? So we'll go through that same logic. Identify the bonds broken and the bonds formed. Okay, what bonds were broken? We've got a carbon-iodine bond that was broken. Okay, we'll skip the next bond that was broken and jump to bonds formed. What other bond was formed? Okay, we've got that carbon-carbon double bond. Okay, so those would be the more obvious things. Okay, but as we compare between these, you might also notice there's a little H plus floating out there. Where did that H plus come from? Had to come from the starting material somewhere. We can't just create matter. So we have to go back to our structure and try and identify where it came from. Okay, the most extended way to do that would be to go through and draw the hydrogen atoms on every single structure you've got. Okay? Does that take a lot of time? Yes, which is why I'm not going to do it. Do I tell you to do it? Absolutely. Okay? You should go through and check each and every single one of the carbons and find out how many hydrogens is on each, to find out where that hydrogen came from. Okay? And since I wrote the problem, I know where it came from. There's our hydrogen. That's where it came from. What was the other bond that was broken? That carbon-hydrogen bond was also broken in this reaction. Okay? Now it gets a little bit more difficult. What kind of name do we want to give to this reaction? Okay? If we didn't know what the answer was, it might be more difficult. Since we know the answer, we'll call it an elimination reaction. Why is it an elimination? We removed pieces from it. We eliminated some atoms from our overall structure, or from our organic compound. Okay? We look at that last one. Same idea. Bonds broken, bonds formed.
How do you know it was that hydrogen?
You would go through and draw on all the hydrogens for every single structure. So in lab, since you're in lab, I'll go through it with you. We'll draw on the hydrogens for every single atom along here, every single atom along here, until we find what hydrogen it was. Okay? I just don't have the space to draw it all on there. Okay? So if we jump to that last one now, sorry, kind of just have to dodge your question at this point. Or let's try it this way. Let's take a vote. You guys want me to draw out all the hydrogens so you can see where that hydrogen came from? Okay, we got 3 or 4, that's enough. So, for those of you listening online, you don't get to see it. Draw it out on your own. Every point is a carbon atom. How many bonds are shown to that carbon? Shown. 1. Carbon's supposed to have 4, which means what else has to be attached to that? 3 hydrogens. We'll go through that same logic on each of those individual carbons. The next one will have just 1 hydrogen. The next one has 2. The last one has 3. I just did. Oh. Two, three, four, 5. 5 carbons, right? Yep. The same logic, the same reasoning on that next structure. Should have drawn it in black. I don't get that. So if we go through and identify the bonds broken and the bonds formed, we'll say formed in green. We still have that double bond being formed. Okay, bonds broken. Since I got red, we'll do that. There's our carbon iodine bond. Okay. Now, which hydrogen do we have to remove? If we removed this one, the hydrogen is going to leave first off as what? Which is more electronegative, carbon or hydrogen? Carbon, which means the electrons in that bond spend most of their time on the carbon. So when the hydrogen leaves, it leaves the electrons behind. Okay? When the iodine leaves, what does it leave? What does it do with the electrons? It takes them with them. So this carbon becomes positive, this carbon becomes negative. So if we removed this hydrogen, where would our double bonds form? Between those 2 unstable structures, or unstable or partially charged particles. Is that where my product was? No. Okay? So we could try and move to the next hydrogen. Okay? This one can't stabilize it at all. I'm not getting into that one again. Okay? Just recognize that we have to move to the beta carbons, so the ones next door, before we can pull off hydrogens. Okay, if we removed this hydrogen, where would our double bond form? Right there. Where does it need to form? Right there in that individual spot. Could it have been this hydrogen? Yeah. Okay. Those hydrogens we're treating as identical, so there are 2 possible hydrogens beta hydrogens that are valid for this.
Is it always one away?
Yes. Okay. What about if we moved here? Okay, if we removed that hydrogen, we could try and we'd build a negative charge on this carbon, but would I be able to get that negative charge, so that's carbon, for those of you, this 1, 2, 3, 4, on carbon 4, would that negative charge be able to stabilize our positive charge on carbon 2? Okay, according to how we have to move electrons, we'd have to move to the bond next door, which means how many bonds would be on carbon, what is that, 3? 5, which means we'd have to break a bond. Okay, what bond do we break? The easiest one to break would be the pi bonds. What did we just make? Pi bonds, where do the electrons go? Right back the other direction. Meaning, that doesn't help you. Does that make sense now?
Yeah, I just, like when you draw them on, you can draw in all these.
So yeah, it comes from the structure and following where those pieces come from.
And if you have the product and the first part too, when you draw it out, you see that there's hydrogen missing on that one, so you know it's where it came from.
Yep. You'd know it would have to come from that one because it's lost a hydrogen here. So if you compared on the other side, if you went from product back to reactant, 3 hydrogens, 1 hydrogen so far matches. Carbon 3 has 1 hydrogen, carbon 3 has 2 hydrogens in the reactant. Our hydrogen has to come from carbon 3. Okay, which is technically the easier way to do it. The way I described it was looking at the mechanism. Okay? Make sense? Okay, so we can look at yet another type of reaction. Have we seen this type of reaction before? Yes, we have. What type of reaction is it? It's acid-base chemistry. So it's nothing new. We've done it a while ago, but it looks different because now instead of it being standard big acids and standard big bases, we're now looking at organic acids and organic bases. So it can look a little bit more confusing, but it is ultimately the same thing. Okay? So what happened in this case? What bonds were broken? The hydrogen to our oxygen. What bonds were formed? Our hydrogen to the nitrogen. Okay? Did I say hydrogen to nitrogen? Yeah. Okay. In this case, I tried to do a better job of drawing those structures to better represent what's happening as they transition. Remember, these two molecules are ultimately really, really, really far apart. And when they get close enough, that's when they react. The electrons from that nitrogen jump out at that hydrogen, okay, and start to share. That hydrogen says, oh, crap, I've got too many electrons around it. What happens to the electron density? Or what happens to the number of bonds around that hydrogen then? One of them has to break. Which bond do we break? Well, if we're trying to make our products, we have to break the one between the hydrogen and the oxygen. Those electrons end up going to the oxygen. Okay? And we end up forming our product. Ultimately, right after that bond has transitioned, the atoms haven't changed location, which is what I tried to do with where those structures were drawn. The structures are drawn in the exact same spot. They haven't shifted. They haven't changed places. The only thing that's changed is where the electrons are in that bond that was either broken or formed. Okay? Does that kind of make sense? So if we were going to classify this one, what do we classify this one as? That's our acid base. So as far as you guys are concerned, we have 3 main reactions. You will be tested on all 3 reactions. You're responsible for being able to both name those reactions and in some of these simpler cases, predict the products or predict the reactants that made those products. Okay? Yes?
I have a question. For the elimination,
Yes?
so if that question was on the test,
Yes?
we would add the bond, the hydrogen bond to it? And then
If it was the exact question, if I asked, tell me the bonds that were broken and formed, yes. You would have to draw that on there because otherwise you can't identify that that bond was broken. Yes. Good question. Other questions about this slide? Okay. So, turns out alcohols can be very, very flexible reactants. So depending on the circumstances they're in, they may act as bases or they may end up acting as acids. So if we take a look at this first reaction, we're We're going to do the same thing that we did on the previous page. Identify the bonds broken and the bonds formed. What bond was broken? I don't quite like just hydrogen. Hydrogen and oxygen bond. What bond was formed? A different hydrogen and oxygen bond. Okay? What did our alcohol act as? So what we would need to do is make sure that we're looking at our alcohol. Our alcohol in this case is over here. What did our alcohol do in this reaction? It donated a proton to another species, which means it acted as an acid. What type of acid? We have a Bronsted-Lowry acid reaction in this case. So when we match up our acid with a base, or our alcohol with a base, that species can donate its hydrogen, and we end up getting it acting as an acid. Okay? What does that mean about the solution itself? So if we took a look at our starting material, okay, so now we'll go through and erase all of those pieces. What happened to the intermolecular forces? So if we were now going to try and apply this to, say, maybe a lab, what intermolecular forces does our alcohol start with? It's the strongest intermolecular force that that compound could exert. Hydrogen bonding. How do you know hydrogen bonding? How would you figure that out? Okay, it's not just that it's got a hydrogen, but that's pretty close. We have a hydrogen attached to an oxygen or a nitrogen, meaning we've got a polar covalent bond. That polar covalent bond can generate dipole-dipole forces. If we have it interact with another molecule, we can actually do a hydrogen bonding interaction. Okay? So this guy up here will generate hydrogen bonding. Okay? So if we were going to predict, say, water solubility, okay, water happens to have what types of intermolecular forces? Hydrogen bonding. So if we're going to look at solubility, we want to look at how those two species interact with each other. Hydrogen bonding and hydrogen bonding, are they similar? Yep. So what does that mean? They would mix well, and we would expect them to be soluble in each other. Okay, potentially. What happens when we move over to the product? What's the strongest intermolecular force now? So what should we look for? Ions. I see an ion up there, which means ionic forces. Okay, what kind of compound is ionic? See if I can come up with a better question. What's another name? There we go. What's another name for an ionic compound? What's your favorite ionic compound? Crap. Not the one I was going for, but acid works. Salts. What do you know about salt? Particularly as far as its water solubility goes. It's very soluble in water. So what happens across this reaction? We started with a compound that we expected to be relatively water soluble, and we end with a compound that is extremely water soluble. Okay? If you see that ionic interaction, you should immediately think, salt, it's water soluble. You could ignore pretty much every other part of the structure. If we've got hydrogen bonding, we've got to evaluate the rest of the structure and see, is there something in there that could counteract the hydrogen bonding interaction? So we'd have to look for covalent bonds, okay, which would generate which kind of force? London dispersion forces. Okay? So let's go ahead and try what happens if, say, we take our acidic molecule, our acidic alcohol, and now what we're going to do is react it with H3O+. Again, what's that? Not yet. I had to change my pen color. And as I say that, notice what pen color I use. What bond was broken? Which hydrogen-oxygen bond was broken?
On the H3O+.
On our H3O+. So what was the... I didn't do a very good job changing the color. I changed my mind. What bond was formed? A hydrogen-oxygen bond over in our product. Okay. What did our alcohol act as? What did it do during this reaction? It accepted a proton. A proton acceptor is referred to as a Bronsted-Lowry base. Okay? If we were going to draw our mechanism, so looking at curved arrows, okay, how would we do that? We don't want to start where our electrons are. So we look in our reactants. Where do we have electrons? On the oxygen. Which oxygen? Okay. Why do you want to put the one on the alcohol as the one with our electrons?
Because the H3O already has two, is already charged.
So there's a couple answers. We could look at our product. Which electrons had to be pushed around? One's on the alcohol, because that's where our bond formed, right? Okay, but let's say we didn't have the product. Both of those starting materials have electrons. Which electron is more negative? The one on a neutral species or the one on a positively charged species? The neutral one. Okay, the positive one is already panicked because it's positively charged. It doesn't have enough electrons regardless of that lone pair. So it's holding really, really tightly onto those electrons. So the electrons that are going to be most reactive would be the ones on that oxygen. That oxygen is going to share its electrons with the hydrogen atom. Where do we draw the arrowhead? On the hydrogen side. How many bonds will we now have to that hydrogen? Two bonds. Can hydrogen have two bonds? Nope. So what has to happen? We have to break a bond. Which bond do we break? We could break the one that we just made, but that takes us the wrong direction, or the other one. So we take the electrons from the bond, so you'll notice where the arrow started in the bond where the electrons were, and we move those onto the oxygen atom. Okay? And we've now shown the mechanistic step for that reaction. Okay? So the big lesson from alcohol, or part of the lessons from the alcohol chapter, is that alcohols react as acids and bases. They have the capability to do both, okay, depending on the circumstance they're in. Okay? We could go through and start to predict that based on our product stabilities. We could look at pKa's, which is what the textbook has you look at, and do some comparisons through there. Okay? We didn't spend a whole lot of time looking at the mathematics on that, so I'm not going to expect you to look too much at that. Okay? Questions about the acid-base characteristics of our alcohols? Okay, next fun question before we move on. Why did I look at the acid-base characteristics before, say, substitution and elimination? Not a bad idea, though. But no, not just background. It's a very particular reason for it. Which chemistry is easier? The acid-base chemistry, which means in an individual reaction, not easy, that's a bad thing to do. Easier, okay? If given an option between acting as a nucleophile or a base, what might we expect the alcohol to do? Might depend on the situation, but what we're driving at is the acid-base chemistry is easier. In most cases, you'd expect the acid-base chemistry to dominate, okay? Because what we're looking at in the acid-base situation is the transfer of what? A hydrogen atom. If we look at the nucleophile electrophile, what are we looking at transferring back and forth between? Not just electrons, because the electrons have to move somewhere. Where are they moving towards? We're looking at a larger structure. So it's not just the motion of electrons, because electrons are moving in both cases. So unfortunately, this wasn't the slide I thought it was. So ignore that. Next slide for the moment. It's not just the motion of electrons when we're looking at a nucleophile or electrophile. We're looking at sharing those electrons with something very, very large. Well, something very, very large already has a lot of electrons. So how easy is that reaction going to be? Not quite as easy because there's already electrons there. So your acid-base chemistry is typically easier because you're reacting with a hydrogen ion. And how many electrons are there to repel away? None. It's H positive, right? There's no electrons there. That chemistry is in general very easy and very, very, very fast. Okay? So when you're put in a situation where you're trying to decide which one is going to predominate, you're looking at your acid-base chemistry dominating over the electrophile nucleophiles. Okay? So then the next fun question is then, can we alter that strength? Can we somehow change the environment of our alcohol to make it either increase in acidity or decrease in acidity, or increase in basicity for that matter? Okay? Sure, why not? Okay, so to be able to do this, we have to evaluate our electrons. Okay? How could we see where our electrons are? Particularly if we're just looking at one structure, we can't look outside it. We are going to have to look within the structure. And if we're going to see how electrons move within the structure, what do we have to look at? Resonance. Okay? You absolutely must be familiar with resonance. So like I said, resonance is going to come back and bite you. Okay? So it's going to play a heavy role in this reaction. So if we're going to look at trying to make our acid stronger, okay, that acid or that species needs to be able to take the electrons away from the hydrogen, which means the electrons have to be drawn inwards towards the bulk of our structure. Okay? So what we've got to do is see, can we draw electrons going into the structure as opposed to out towards the hydrogen? So if we look at this first case, okay, do we have electrons? Yes. So let's attempt resonance. Okay, hydrogen can't accept any more bonds, so let's not push the electrons towards it, because that's going to do the opposite of what we want anyway. Let's push electrons away from it. So let's move them downwards, okay, away from that hydrogen. We're trying to see if we can make this a stronger acid. Can we steal electrons away from it? Okay, well, what happens if I move the electrons in there? What have I formed? A double bond. How many bonds would that carbon then have? Too many. I only see 4 there. There's an implied hydrogen. Implied hydrogens suck. Watch out for them. Okay? Which means how many bonds are at that carbon? 5. We have to break a bond. The only bond we're allowed to break when doing resonance is a pi bond. Do we have a pi bond? Yes. So what do? We take those electrons and we move them right back. What's the net result? There's our net result.
There's nothing up there.
Exactly right. No resonance. Okay? That structure does not have the option to be resonant, which means that's pretty much our baseline for our alcohol acid-base characteristics. Okay? So now what we want to do is move to the other structures and see what happens in those cases. Okay? So again, same idea. We're going to start with our electrons. Where do we have electrons? Why do we pick the oxygen and not the pi bonds? Those are the electrons we're ultimately concerned about in this case, is that oxygen and the electrons it's sharing with that hydrogen. We want to take electrons away from oxygen. So it makes more sense to start there. So let's move our electrons downwards. How many bonds would that carbon then have? Or that bonds would be in that space? 5. That's a problem, right? So we have to break a bond. What bond are we allowed to break in resonance? Pi bonds. Do we have multiple pi bonds to choose from? Yes. So what pi bond are we going to break? And we're going to move those electrons from a bond to an atom. Okay, we won't do bond to bond because that's only going to repeat our issue all the way around this structure. Okay, so in this case, we're just going to simplify as best we can, go bond to atom. What's our net result? Yes, it's going to look naked again. Not quite yet. Oh, shoot, I can't do it on here. Should have left that drawing, sorry. Our result, let's try that again. We've got our cyclohexene, or benzene ring. We didn't touch the other double bonds. We've got a double bond up top between the oxygen and our carbon. That oxygen still has a lone pair. Wow, this looks pretty quality. Okay, and we've moved electrons onto that carbon. Okay, what charge is the oxygen now? Positive. Does oxygen want to be positive? What's it going to do? It's going to take electrons. What's a nice, quick, easy source for it to get electrons from? The hydrogen. What have we just shown? We've shown resonance, but we've also shown what about that oxygen-hydrogen bond now? What's special about it in comparison, say, to the other one? It's more polar, meaning that hydrogen is more acidic. It's closer to being H+. What does that mean? This structure is a stronger acid than our standard alcohol. Okay? It's a stronger acid than this one. Because what we've done is taken the electrons on that oxygen and pulled them away from the hydrogen. We pulled them into the structure. Okay? That hydrogen now doesn't have the electrons that it needs to stay bonded, so what happens? Goes off to find them someplace else as H+. Okay, so we've made it a stronger acid. What happens in, say, the next case? So again, we're looking at that oxygen-hydrogen bond. We want to see if we can make that even more acidic. Okay, this one requires a lot more work. What we'll do is take our electrons from our oxygen, move them downwards. Okay, except this time I'm not going to stop my arrow going from bond to atom. I'm going to go bond to bond. Okay, what does that mean about this carbon now? Too many bonds, right? So we're going to have to break a pi bond. Do we have yet another pi bond there? Yep, so we're going to break that pi bond and move it bond to bond again out to that nitrogen. Why would the electrons go towards that nitrogen? The nitrogen is positively charged. Good job. How many bonds does that nitrogen now have? 5 bonds. Can it have 5 bonds? Do we have another pi bond we could break? Yes. We'll push it all the way out. Okay. What have we done? We've increased the possible resonance structures. Okay. We can pull that electron density even further into the structure because the functional group down at that bottom really wants electrons because that nitrogen's positive. It starts sucking electrons like a vacuum, okay, through the middle of the benzene and pulls them even further away from that oxygen-hydrogen bond. If there's less electrons in that bond, what does that mean about the strength of that bond? Becomes weaker. If it's a weaker bond, what does that mean about the acid strength? It's even stronger.
So would that H come up again?
Yep. And we'd be looking at the strongest acid of those 3.
Is that happening because you're creating a double bond between the oxygen and that carbon, so it's going to pull the electrons from the hydrogen so that
Yes.
it has
So it stabilizes the positive charge that could form on that oxygen. Okay? So what we're trying to evaluate is how we can change the structure. Okay? And in this case, what we're doing is we're evaluating our acid characteristics, trying to take the electrons away from that hydrogen faster. Our other option is doing the acid-base reaction. Get rid of the hydrogen. Okay? If it's a stronger acid, or if it's an acid, it's going to take off the H+, and it's going to leave what charge behind? We take off H+ from a neutral structure, we're going to be left with negative. Okay? If it's a stronger acid, what can we say about that negative charge? It's more negative or less negative? Okay, let's take a look at a couple strong acids. What's your favorite strong acid? So if we take a look at hydrochloric, that's what you said, right? If it acts as an acid, what's our product? We get plus and Cl minus. What if we had HI? What is HI? Yeah, good call. It's also a strong acid, right? So we dissociate into H plus I minus. Which is the stronger acid? HI. Why is HI the stronger acid? If we look at the difference between these, both of those hydrogens are positive, Both of our chloride and iodide are negative. What's the difference between chloride and iodide? Size and electronegativity. What trumps? Size. So if we take a look, we'll make it excessively exaggerated. Chloride is smaller than iodide, so here we go. Here's our chloride ion. The charge is ultimately the same, so it's still a single electron. So let's draw the single electron in there. Okay. Let's look at iodide, much, much bigger. Still with a single electron. What comes out of the outlet? Electrical outlet? Electrons. We don't stick our finger in the electrical outlet because it hurts, right? You get shocked. So what happens if you touch that electron? It hurts. You now have to stick your hand into one of these two atoms. Which atom do you stick your hand into? Iodide. Why? Less likely to get shocked. Why? That electron is now spread over a much larger area. We've stabilized the negative charge by spreading it over a larger area. Why do we expect this species, okay, our third one here, why is that one expected to be a more acidic structure? Because if we look at the product, if we look at our negatively charged species, our conjugate base, we can take that negative charge and we can displace it through the entire structure. Okay? And it's through an entire structure that's bigger than the previous one. Which means I've displaced that negative charge over a larger area, meaning my conjugate base is more stable, which means what about the acid becomes stronger? Okay? Is that kind of making sense? What happens? Not sure how. Oops, I didn't mean to do that. I don't want to look at stronger bases in this case because while this is a stronger base or stronger than the middle two, it's not stronger than the last or than the first one. Okay? So we won't look at making your alcohols more basic. We'll treat them in general as acids. We can force them to act as bases, okay, with fairly mild conditions or relatively mild conditions. Okay? But for the most part, we'll see them as acids. Okay? For instance, functional groups. What's a carboxylic acid look like? Right? What is this group right here? Oh, that looks an awful lot like an alcohol. Why do we end up calling it a carboxylic acid, not an alcohol? Because the proximity to this changes the reactivity of our alcohol. Okay? We'll look closer at carboxylic acids at the tail end of the semester. Okay? But you're ultimately recognizing that your alcohol in a carboxylic acid or the OH group becomes more acidic for a very particular reason. And it's because of the conjugation within this system. You can again try resonance with your conjugate base and see what's happening there. Okay? Could we even further mess with our acid-base chemistry? Okay, well, instead of adding things around the alcohol, let's just straight up change the atom. Instead of being an oxygen, let's make it a nitrogen. Okay? Does that change our characteristics? So if we go through and do a comparison between these, we got lone pair electrons on both. The hydrogen is an or is attached to an electronegative element in both. Okay? So what might we expect or predict for the amine or our NH structure? Would we expect it to act the same, both as a base and an acid? On the surface, it seems relatively fair to go ahead and do that. Nope, I didn't think I had one there. Turns out that our nitrogen is not quite electronegative enough to steal the electrons away from the hydrogen. Okay, well, if it's not quite electronegative enough, what does that mean about the partial charge on the hydrogen? Does it become more positive or less positive? Less positive, meaning it becomes less of a strong acid, less acidic. Okay? So if we're going to look at our reactivity, when we move to an amine, we don't have the acid characteristic. Okay? we still have that lone pair of electrons. Okay, so it still could potentially act as a base. Would we expect it to act as a better base or a weaker base? So stronger or weaker? Okay, stronger, why? I don't like that answer. Give me a different one. Okay, what does our lone pair have to do? The nitrogen and the oxygen, for it to act as a base, what do we have to do with that lone pair? We have to share it. What's the difference between oxygen and nitrogen? Is there a difference in size that we need to be worried about? Nope. So it's only electronegativity. Electronegativity is what? The ability for an atom to attract bonding electrons. So hold the electrons it's got. Which atom is more likely to donate electrons? The one that's higher in electronegativity or lower? Lower. What ends up happening? Our amine is a better base. Okay, or a stronger base because of the lower electronegativity. I'm going to regret writing that there. There we go. Stronger base. All fits. Okay? So that's our big characteristic jump when we move there. So of course, just like we did with the alcohol, we now want to go through and address, can we make it an even stronger base? Can we mess with the acid-base characteristic? Well, what do you think? Sure, why not? Of course we can. Okay? So let's go through and evaluate these. In the first case, we're looking at a standard situation, so nothing particularly special. Okay? We can't do anything with that lone pair. If we tried to move it into the structure, okay, we'd end up forming a double bond. Can we fix that? That carbon then has too many bonds around it, so we'd have to break a bond. What bond can we break? We have to break the pi bond that we just formed, which means no resonance. Okay? How about we move to the next one? What happens in that case? Let's go green. Why not? I can move those electrons down just as we tried before. Okay? Which would mean how many bonds would that carbon then have around it? 5. What do we have to do? Break a pi bond. Do we have a pi bond that we can break?
Yep.
Other than the one we just formed?
Yep.
Yep. So what we can do is take those electrons. We'll move bond to atom. Okay. What have we done? What did we do with those electrons? We moved them where? Into the structure, right? So onto the carbon. If we move the electrons into the structure, what does that mean about its base characteristic? It's going to be a weaker base. We need those electrons to go out of the structure, to go react with a hydrogen. If we're pulling the electrons into the structure, we're doing the exact opposite of what we would expect. So if we now compare those two species, 1 and 2, here, 1 and 2, our stronger base is the first one. Okay? And it's because we've pushed those electrons in that second structure, and we moved them into the structure, which is the opposite of what we wanted to do. Okay? What should we be looking for if we find a strong base? What would we hope to see? What would be a big red flag for a strong base? What does a base need to be able to do? It needs to be able to accept a hydrogen. What's the charge on a hydrogen? Positive. So what's the charge on our base need to be? It needs to be negative. So a big red flag for a base would be a negative charge, because it needs to be able to react with that hydrogen. Okay? So let's take a look at this next structure. Okay, and I was kind of a jerk on this one, and I didn't draw the lone pairs. So if we add those lone pairs on there so we can see them. Ooh, that one was coming out gimpy. Okay. We have electrons. We want to see what we can do with these electrons, so let's start moving them around. Okay. Which pair of electrons is going to be the easiest to move? Left or right? Right. Okay, if we take the right one, where are we going to try and move those? Up or down? We try and move it down. How many bonds are around that carbon? 5. Is that a good thing or a bad thing? It's a bad thing, so we have to break a pi bond. The only pi bond we've got? The one we just made, which means bad choice. Try again. So let's go up. Okay, how many bonds does that carbon now have? 5. Okay, because we got the double bond. So we've got our double bond that's already there. There's 3, 4, and we just made a 5th one. So we have to break a bond. What pi bond do we break? We've got another one. It's right there. What's the net result? The exact same thing. So is the rightmost nitrogen doing any resonance for us? No. Okay, well, what does that mean? Let's try the left one. Okay, so let's move to the left one. We've got those electrons. Where do we want to move them? We move to the left. How many bonds does that carbon have? 5. Do we have a pi bond?
No.
Not a different one, so we move it right back. Net result is nothing. So where else can we move those electrons? Down. Let's try down. How many bonds does that carbon have? 5. Is that a good thing? No. So what do we have to do? Break the pi bond. So we have to move right back to where we started. So where else should we move it? Okay. We move it there. How many bonds does that carbon now have? Come on. Has 5. Do we have a pi bond that we can break? Yes. Where's that pi bond? So we're going to take those electrons and we're going to move them bond to atom like we've done before. What happened to this nitrogen in this reaction? Became positive because it gave up electrons. So it started neutral, donated electrons, so it becomes positive. So it's partially positive. What happened to this nitrogen? It started neutral and it gained electrons, so it's partially negative, right? Gained electrons. What does that mean about the base characteristic of that nitrogen? It's more basic. It is the strongest base on this page. It would be the most acidic, yes. It is still not acidic. Okay? Do not treat amines as acids. Treat them only as bases. Okay? When might you see a nitrogen that's acidic? Any guesses? There's a nitrogen. There's our hydrogen. Why would this nitrogen act as an acid? It's got a positive charge. It wants to get rid of that positive charge. It's going to take electrons from one of those hydrogens. Okay? It's the only case where you'll see nitrogens act as acids, when they're forced into a positively charged state. Okay? Questions about that?
Would
Yes.
the third one even happen? Because don't they all just want to be neutral? Why would they
So-
move around to get partial charges?
So that's a very, very good question, is trying to decide which structure ends up being the best structure. So I don't have the space to draw it there, so we'll draw it up here. Oh, man, this doesn't remember greens. Doesn't have to look pretty, as long as it's there. So, why would we see this structure? So if we're now going to compare resonance structures, let me erase all of that. Okay. Why would we see, or why would we ever look at this structure as opposed to the circle one? Okay. If you were asked to draw a Lewis structure, which one would be your correct answer? That one. Why? You're right. It's neutral. Okay? This one is our best structure. So we'd want to draw that. So why do we draw the other one? We want to find the reaction. We want to find how that molecule can react with other molecules. So this is a possible resonance structure. It's a bad one. But one of the nice things about resonance, okay, is if you've got it, it will show you the reactivity of your structure. We now know that this compound, or that nitrogen, is relatively basic because it is partially negative, or it's negative in this case, whereas in these other cases, it was not. Okay? So we've put more electron density onto this nitrogen than we could here. And because of that, this nitrogen becomes basic. So why do we draw it? We draw it because we're trying to find the reactivity. We're trying to find what we can do with it. Okay? And yes, that takes us to a structure that's bad. But that's irrelevant. All we're trying to do is to see what chemistry we can do with it. And it hasn't invalidated any rules. We still have octets. Okay, so it still shows us our chemistry. Or it shows us our chemistry, whereas in this one, it doesn't. Okay, so the only reason we move to that resonance structure is when we're trying to find out what reactivity can it do. That's why we push to our resonance.
So if it was like just by itself, it would just be that.
We would be looking, the best structure to draw would be this. Okay, and that's the other thing that's obnoxious about chemistry. If we could zoom all the way down to the smallest scale, does our structure look like that? No. What does it really look? I'm not sure I can even draw it on here. Let's see what I got. What we would do is kind of draw our electron density. So it's this giant kind of ballish thing. Okay, so we got a lot of electrons around in those balls. Bonds. I said bonds. The nitrogen is electronegative. Shush. The nitrogen's electronegative. So what does that do with most of the electron density? It gets attracted to those areas. And in particular, we'd see a lot of electron density out on that other nitrogen. Why would we have more electron density out there? Because one of our resonance structures shows that it can put more charge out there. So what we're trying to draw with these three-dimensional structures, or line angle stuff, is as close to the actual model as possible. Okay? So, other questions? Okay, so we'll go ahead and move on, please. So, our overall acid-base summary, we're looking at Bronsted-Lowry. I keep forgetting to make sure I add that to each of these slides. And when I'm referring to acid-base chemistry, 9 times out of 10, I'm referring to the Bronsted-Lowry definition. I'm not referring to the Lewis definition. Okay? If we're going to summarize everything that happens with our Bronsted-Lowry definition, we first off need hydrogens. So what we can go through and do is look at our classic examples. Fluorine we typically ignore as far as a reactive atom because it just does crazy stuff, so we kind of ignore it. So we can move to chlorine as our first representative element within the halogens. Then we can compare oxygen, nitrogen, and carbon. Okay, if we add a hydrogen to our halogens, that can only act as an acid. So if we were going to compare our reactivity, our halogens only act as acids or leaving groups. We could potentially see them act as leaving groups if they aren't attached to a hydrogen. Okay. What happens with the bases? Well, the bases can act as either acids. The alcohols can act as either acids or bases. Okay, so we're starting to transition away from that reactivity of our halogens. Okay. Then nitrogens, okay, become even less reactive. Less like the halogens. The halogens were acidic. So what does that mean for our nitrogens? Become basic. Okay? Until ultimately we can move all the way to carbon. And in the case of carbon, they are so unreactive that they're neutral. Okay? They don't have the electrons. They don't have the electrons to donate out to act as a Bronsted base. And they don't have the electronegativity to steal electrons away from hydrogen. So they can't act as an acid. Okay? So if you kind of remember that general trend, your acids start, I meant to match it to the periodic table, sorry about that. your halogens start on, what's that, your right-hand side of the periodic table. There's where your acids are. As you transition leftward, okay, you start to become less reactive, okay, and you move away from the acidity. So you go starting to become more and more basic until you reach your oxygens, where you get a mix between acids and base characteristics. Then you move into the nitrogens, which have lost all that acid characteristic. And then we move into the carbons, which just can't react. Okay? They've just become neutral. Don't ask me to keep going beyond that, because that messes with things. Let's stick with the pretty pattern. Okay? Yes?
So if we went down the periodic table underneath each of your examples, all of the elements would react the same, like sulfur
Very
would react
similarly.
the same as oxygen?
Yes. Okay? And since you asked that question, in theory you guys all know this already, it's exam 1. If we went from what am I looking for? My eraser. If we were going to compare these two bonds, hydrogen, oxygen, hydrogen, sulfur. Which one was more acidic? What's the difference between oxygen, shouldn't have erased that, and sulfur? Size. Size trumps. So what we're looking at is a large atom with that electron in it, a small atom with that electron in it. Which one stabilizes that negative charge better? The larger atom. Meaning this is more stable than this, which means what about the acidity of that hydrogen? It's more acidic. Okay? Build like a little collar and just carry it around. Okay? Questions about our acidity. So I'm pretty sure that's all of the acidity that you'll see, well, from the alcohol and from Chapter 8, Chapter 10. Yes?
So the more stable, the more acidic?
The more stable the conjugate base, so the more stable the products are, the more acidic your reactant was. Yes? Yes. Okay. So you can tell that this slide was perfectly set up and ready to run. So what we're looking at here, and I actually want to delete these so I can draw. Come on. Exit show. What the heck is going on? Okay, well, while I'm waiting for that to figure out what the heck it's doing, make some guesses. Oh, I think I killed it. Nope, there it goes. Stupid computer. Chemistry, we were looking at there. Play from current slide. 2. Give it. Faster. So, misleading alcohol substitution reaction. So if we take a look at butyl iodide, which was the first reaction on there, and say we wanted to go through a substitution reaction with our chloride, okay, what would our product look like? Officially our iodide, right? Okay, so we ran through a substitution reaction there. Okay, the chloride swapped out for our iodide. What happens if instead of it being an iodide, we move to an alcohol? And we add chloride. Okay. One of the things we said about the alcohol functional group, okay, is that we still have that highly electronegative element, so if we're going to look at that bond, okay, between our carbon and oxygen, oxygen is very, very electronegative, so what happens to its charge? Becomes partially negative, tracks the electrons towards it, which means what happens to the carbon? Partially positive, just as if that oxygen was a halogen. Okay, so we've got an electrophilic carbon. Okay, so what might we predict from this reaction? Chloride's negative, right? Where's that negative going to want to go? To a positive. Where's our positive? On that carbon. So we might say that, hey, this looks like a reasonable idea. And we'd have OH minus, right? So a nice substitution reaction. Okay, one of the things that we didn't stress too much about when we looked at our alkyl halide substitutions was the stability of the leaving group, because we were looking at halogens leaving. And all halogens were stable leaving groups. Why are halides or halogens good leaving groups? They're happy by themselves because they can stabilize that negative charge because they're high in electronegativity, and most of them are fairly large. Oxygen may be high in electronegativity, but how big is it? It's not very at all. Okay? In fact, it's one of the tinier elements that we deal with organic chemistry. Okay? Which means we've got that negative charge, okay, on an electronegative element, but we said size is really, really important. We've got that negative charge on a very small atom. How stable is that? Not very stable at all. And what ends up happening in this reaction? You get no reaction. Okay? So we have to be aware not only of just, hey, it's a substitution reaction, we can just substitute. We also have to be aware of the stability of the leaving group, and that's the biggest aspect for our alcohol chapter. So when we're looking at substitutions, we have to make sure that leaving group is a better leaving group. Okay? So in this case, what we're trying to do is convince that oxygen to take the electrons. Okay? And it already has, come on, 2 lone pairs, right? So how can I make oxygen want to take electrons more? I want to make it positive. If I can make that oxygen positive, it's going to get pissed, and what's it going to do? Steal electrons from its best, easiest source. Okay, so what is something that I can do to make that oxygen have less electrons around it? I want to have it share its electrons with something else. But that something else has to be something quick and easy as far as chemistry. We learn any quick, easy chemistry that we spent most of today talking about? Acid-base chemistry. We said our alcohols can act as acids or bases. In this case, we want that oxygen to act as a base. We're trying to take electrons away from it. Okay, so we want it to act as an acid. Base. Frick. So to make it act as a base, what do we need to add to that solution? We need to add an acid. And what we'll add is a strong acid. What's a good favorite strong acid that might also happen to supply our nucleophile? How about HCl? So if we add HCl, now what happens? Okay. We've got a very strong acid with that H+, and we've got our basic oxygen. So what's going to happen? The oxygen is going to share its electrons with the hydrogen. How many bonds would that hydrogen now have? Too many. So what does it have to do? What bond do we want to break?
The HCl bond.
Probably the HCl bond. Okay. What does that produce? What's our product in that case? And then our Cl minus, right? Is that a stable product? Why not? It's positive. So that oxygen is now pretty pissed off because it's positive. It wants to be neutral. So what does it need to do to become neutral? It needs to get some electrons. Where's the easiest source to get electrons? Hydrogen, good answer. It can take electrons from that hydrogen, which means what happens? Hydrogen goes off and we get the reverse reaction. This is an equilibrium reaction. Okay? That's not very productive for us, so what do we hope happens instead? Takes it from the carbon. Yes. It just happens less frequently than with the hydrogen. Okay? What's the result in that case? What have I shown? I've got water, so I can accept that. Have I done anything with the chloride? I've just run out of space, I think, on this. Yep. Have I done anything to, say, this carbon? No, so let's draw that on. How about the next one? How about the next one? Kind of, sort of. So that middle carbon I did something to. What did I do to it? I took electrons from it. That's all I've done so far. Which means what happens to it? It's formally positive. How can I stabilize that positive charge? With electrons. Where can I get electrons from? I can get it from the chloride or the oxygen. If I get them from the oxygen, what happens? You're really good at these reverse reactions. Okay? We could get it from the chlorine. The chlorine could come in, and now what's our product? Now we've done our official substitution. Okay? So for our substitution reactions to occur with our alcohols, okay, we have to go through an activation step first. What is that going to mean about our elimination reactions? Elimination reactions with alcohols. What are we going to have to do before we do an elimination reaction with an alcohol? We're also going to have to activate it. Okay? The OH group does not act as a good leaving group. We need to make it better. To make it better, we have to add a hydrogen to it to make it a good leaving group. Once it's a good leaving group, it can take the electrons. So with all alcohol substitution or elimination reactions, we have to activate that alcohol. We have to activate that oxygen to force it to react. Okay? Questions about that? All those pens work? Okay, according to my clock, I've got a minute left, so I think we'll go ahead and leave it there. So as far as what you can expect on the exam, we'll go up through substitution reactions with our alcohols. We won't cover the elimination reactions with alcohols, so you don't have to worry about that. All acid-base chemistry with your alcohols and your amines will be on there. Nomenclature for amines and alcohols will be on there. You've got RNS, you've got stereochemistry, all that fun stuff. Okay? I went through and posted a couple things on